In today's lecture, we're going to be going over floating point instructions in assembler. Now, it's a kind of aspect of assembler that I think many of us may not have anticipated if we've learned to program in a more simple high-level language to start with. And that's simply because the way, for example, I add numbers or store numbers, whether they be integers or doubles, doesn't really fundamentally change that much if I'm coding in C++, for example. Sure, I have to define a type that is different, but fundamentally I don't have to really change the way in which I interact with the calculations that relate to those numbers. However, when we get down to a machine level, we have to actually make the distinction whether or not we're performing a calculation on a floating point number or rather on an integer. And with that in mind, we're going to now go into how we actually perform floating point calculations in an assembler context. So how does the CPU perform these floating point calculations? Now, PC floating point operations were actually at one point in time done on a separate chip. Specifically, the first of its kind, or the first mainstream one of its kind rather, was the 8087, which was dedicated to performing floating point operations, with having the 8086 chip focusing on normal integer-based calculations. Now, this 8087 chip actually worked on a kind of interesting floating point representation. Specifically, it managed a stack of floating point numbers, and each of these floating point numbers were actually 80 bits in size. So it's kind of an odd size floating point number that they had at the time. In some sense, overkill if you were to use the whole 80 bits, but there were subsets of which you could use for specific calculations if you wanted to use a 32 or 64-bit version as well. Now, this stack and the instructions that work on the stack directly do still exist in modern architecture. Now, the x86 design philosophy really has been that as soon as they've advanced and added more instructions, they try to never deprecate older instructions. So the original floating point instructions that relied on a specialized floating point stack and its corresponding instructions still exist, but they're largely ignored on a modern system. I bring this up because it is possible that you'll encounter a tutorial here or there where they use these old instructions. However, for this course, we're going to be using the new floating point instructions exclusively, so your answers have to be in relation to that. And the same thing in the context of your pracs and similar things like that, and that will assume you're using the new operation. So keep that in mind. Obviously, this is in keeping with what the actual trend is with current instruction use. The other approach is simpler, but it is definitely not what is used in practice anymore. Now, in the absence of an 8087 chip on an older system, back when it was dedicated to just perform floating point operations, you would be forced to emulate floating point calculations in software or at a software level to achieve them. However, that's obviously not conducive to effective computing, which is why they added the separate chip. And on modern computer architecture, floating point operations are done by the same chip as the integer component. Obviously, there's different microarchitectures for different parts of it, but it's not a separate entity as it was at one point in time. Now, x86 64-bit CPUs have 16 floating point registers at our disposal, which we can interact with in a fashion that is somewhat similar to how we've interacted with our other registers. These floating point registers come in two mainstream sizes, 128 and 256 bits. Now, that might sound a little bit oversized, considering that we know that a float is 32 bits and a double is 64. So why are these floating point registers so large? And the reason is that they're actually designed to be able to perform single instructions or single calculations like additions or multiplications and the kind, or perform packed versions of those instructions. And that's where we come into the area of SIMD instructions, specifically single instruction, multiple data. Okay, the idea being instead of adding two numbers together in a single instruction, we can actually add a set of numbers together using a single instruction, which we'll get to as we go forward. And that's why we're actually focusing on this newer version of floating point registers, because it allows us to naturally perform SIMD operations. And utilizing SIMD instructions is actually kind of a necessary component to effective numerical calculations nowadays. So we're going to focus on these new registers, and as I said, all tests and other assessments, we will exclusively use these newer registers. The older instructions, you will be able to identify them because they tended to start with an F for floating point, and they were often accessing a register with names like STO to indicate that you're working against the floating point stack. Again, we're not going to focus on that. We're going to focus on the new registers. And there are two flavors that are kind of relevant to us. There's the XMM version of the register, which goes from 0 to 15. And then we have the larger version, which is the YMM register, which also goes from 0 to 15. Now, what is important to keep in mind here is that this XMM0 is 128 bits, the YMMM0 is 256 bits, but in a similar way to which the EAX register was the bottom half of the RAX register, the XMM register is actually the bottom half of the YMM register. So they're actually part of the same register, with the one just being larger. Okay, so the YMM being the larger of the two, specifically it's a whole 256 bits, whereas the XMM version is only 128 bits. Now there's actually a third version which the textbook doesn't actually discuss, which is the ZMM versions. Now, we're not going to go through the instructions for them. It's somewhat regarded as a very niche type of floating point register. So that ZMM register is actually 512 bits, and it's something that Intel has really pushed hard on as like another selling point, particularly the Xeon line processors. However, it's really not the most commonly used instruction in mainstream compute, and it actually is to such an extent that you'll find a couple of videos on YouTube of Linus Torvald, the guy that invented Linux, actually criticizing Intel, saying that these AVX 5112 instructions are a waste of time and it's wasting silicon on his CPUs. So it's a bit of a point of contention, the ZMM register. So our focus is on the XMM, so the 128-bit, and the YMM, the 256-bit registers. Now there are 16 of these floating point registers, as we said, and they scale between 0 and 15. So here we have our YMM0 to YMM15. These are referred to as the AVX registers, for the Advanced Vectorized Extension registers, and each one is 256 bits. And the lower half, as I indicated in the previous slide, of these 256-bit registers actually corresponds to the XMM register with the corresponding integer. And again, this simply ranges between 0 and 15. These are referred to as the SSE registers. Okay, so these are kind of mnemonics that you'll encounter if you look at new CPUs, because they make it quite clear of what type of instructions of this nature do they support. However, any CPU that you're likely to be working on will support both of them, but just for the sake of completeness, any Core i series CPU and the corresponding AMD equivalents. So if you think about the year of this, I think this is 2007 when the first Core i series came out, will support the whole AVX 256 instructions, so the YMM register, so you won't have an issue. But for the sake of most practical tasks, you'll get away with the XMM versions, but you need to know both in terms of the theory. Now, something I want to maybe make explicitly clear is that I'm going to, and as the book does, mainly discuss the instructions for floating point operations in terms of the XMM registers. And the reason for that is that all that has to change if you want to be working with the YMM registers is you append a V in front of the instruction. So everything you'll see that I'm about to discuss, if you instead are working with a YMM register as opposed to an XMM register, you simply add a V in front of the instruction and it will work exactly the same, with the obvious distinction that now you're working with a larger floating point register. Now, something that I think we need to make very clear is the nature of the layout of these registers. So let's just discuss this in terms of the XM register for simplicity. Here is just a pictorial example of a badly drawn register, which we can call, let's say this one is our XMM0. 0 register. Now, obviously, I might want to be storing a floating point number that is much smaller than 128 bits, with the two standard ones being 32 and 64. So how does this register actually get laid out? Well, the bottom 32 bits could be used for one floating point number. Okay, so say I just wanted to store a scalar. It would just be stored in the bottom 32 bits of the XMMO register. And in that situation, the top part would be in essence ignored. In the same kind of vein, if I wanted to store a 64-bit register, or rather a double floating point number, I would be using the bottom 64 bits of the XMM register, and the higher order bits will be in essence not used. However, we can also use these XMM registers to store multiple floating point numbers. Specifically, because I have 128 bits at my disposal, in the case of XMM, I could store 4 floats, or I could store 2 doubles. Okay, that's simply because obviously 4 times 32 is 128, and the same token 2 times 64 is 128. Now in that situation, I would partition my register into the corresponding number of components. So say for example, I'm talking about this 4 float example, I would have 4 chunks in my register, where this is the first floating point, the second floating point, the third floating point, and lastly the fourth floating point, all being 32-bit numbers in my XM register. That's how the register structure is. So how do we actually distinguish between what type of operation we're performing? Because these registers can store just one value, which we typically refer to as saying it's holding just a scalar, or it could be holding a vector of values where we have to perform slightly different types of calculations. Okay, now that vectorized version where I have multiple values is often referred to as a packed version of an instruction. But before we get to the packed version, let's just talk about moving floating point numbers between registers if we're just talking about scalars. So here we have 2 instructions for the XMM flavors of these instructions. We have move SS and move SD. So how do we interpret these mnemonics? Well, obviously MOV is our good old move. This S over here corresponds to scalar, and the last S there corresponds to single. Now, single is kind of an equivalent term for a float. So single means 32 bits, and it means the same thing as simply being a float. If instead of having a S there, we have a D, this simply means double for double floating point precision. So this was single precision, and this was double precision. Okay. Now, depending on what size floating point number we're working with, we have to specify a different type of instruction. We have to make that explicit. Okay, and the reason that happens is because of the way in which these moves occur. And I'll show this to you when I get to some more examples, in that with a typical integer-based move, the assembler could infer how big the register was going to, or how big the value was based on the register you were loading it into. However, in this context, I will be moving into, say, XMM0, even if I'm talking about a single or a float, which is why I actually had to make it explicit if I'm talking about a scalar or a double. Okay. Something that we should maybe make kind of explicitly clear is that it should be noted that there is no implicit data conversion when working with these floating point numbers. Now, the old instruction set actually could automatically do some degree of conversion, but this means that if I, for example, have an integer value that I want to treat as a floating point value, I actually have to call a specific instruction to convert that integer to be in the corresponding floating point format that I need. So we'll show you what these instructions are shortly in this lecture, but I just want you to keep that in the back of your mind, that we have to explicitly convert an integer to a float if we want to use it for a floating point type calculation. So let's look at a couple of moves. So the instructions that are below follow the standard pattern of having at most one memory address. And here we have a couple of examples of moving scalars. So this first one over here, I'm moving the value at X into my XMM0 register, and you'll see that the value at X is in fact a double data word, so it's 32 bits. Now, once again, if this is my XMM0 register, and I'm loading in this value is going to go into the bottom 32 bits. So the bottom 32 bits of XMM0 are going to represent 12.35, obviously in the IEEE floating point standard format. Okay, let's say I want to try and move something from a register into memory, similar to before. In this case, I'm going to be moving a scalar double, and I'm going to be moving it from XMM1 into the memory location Y. Okay, so you'll see in this example, Y already held a data quad, so it had 64 bits of space ready to go, and we're loading from XMM1 into it. Now, again, just to reiterate, if I have XMM1, because I'm performing a scalar double move, it is going to use the top 64 bits, sorry, rather the bottom 64 bits of XMM1, and load those into Y. So you'll see it will now use 64 bits. Now, if I had incorrectly had, say, a 0 over here, so say there was 0 and I had previously loaded, and I tried to move that value into Y, I would have ended up getting likely a somewhat garbage result because I would have tried to use more bits than that 12.35 was actually represented using. So again, as with most assembler, we always have to keep sizes in mind. This last instruction here simply moves from XMM0 into XMM2, and because it's moving a scalar single, it will copy the lower 32 bits from XMM0 into XMM2. Now, we obviously would like to be able to utilize the vectorized versions of these instructions, or more specifically, work with packed data. Now, I mentioned earlier that the XMM register is 128 bits, so it can hold 4 floats or 2 doubles. There's also vectorized versions of integer operations. We're not going to discuss that in this course, so don't worry about reading further into that area. It's not in the textbook either. And if I, for example, was working with the YMM registers, I would have 128 bits, which means I could work with 8 floats or 4 doubles simultaneously. Now, there's a little bit of an extra consideration when working with packed data that we didn't have to worry about when we were talking about moving around simple scalar values. And that is that we have to figure out what type of move we want to perform. Now, that sounds a little bit odd, but there's actually 2 types of packed moves we can perform. The one is called an aligned move, and the other is an unaligned move. An aligned move means that the data we're about to move into, say, a register, or out of a register, is on a 16-byte boundary, so the address is a multiple of 16. If we use an unaligned move, we don't need to worry about having that 16-byte boundary alignment. So now, given the presence of an aligned movement with a restriction and an unaligned movement with no restriction, why would we use the one with restrictions? And the simple reason is that it is considerably faster. The degree to which it is faster is less severe on modern architecture than it was on older architecture. That said, it is still notably faster to use an aligned move. And this aligned move is exactly why we need to preserve the 16-byte alignment when we start talking about correct function construction, like we discussed in the previous lecture, where we had to actually push an extra thing onto the stack to ensure that the stack was always on a 16-byte boundary. And we did that such that if somebody used a calculation that assumed we started on a neutral level, so multiple of 16, that it could perform aligned moves if it was so intended or desired. Okay, so that's why we had to preserve that 16-byte alignment. Now, what's the downside? What happens if I try and perform an aligned move and my data is not on a 16-byte boundary? What would go wrong? Well, very simply, you will get thrown a segmentation fault and your entire program will crash. So it's not a very easy error to recover from. And you may also not anticipate that error coming back out. But in essence, what will be shown to you is that you've just received a segmentation fault. And it's because you made an inaccurate access to memory. Because remember, it assumed a multiple of 16, it wasn't, so internal calculations are obviously going to go awry because it was relying on that assumption, and hence you end up with a segmentation fault. So how do we perform this type of move? Or how do the instructions even look? So here we have MOV again to indicate move. The next character, we have two options, either an A for an aligned move, or a U for an unaligned move. Okay. The next character here is P to indicate it's going to be a packed move. And then we have the last one to indicate the size. So this will be a aligned move of packed values. Specifically, the values I'm moving are scalars, or sorry, singles. So these will be floating point numbers or 32-bit numbers. Now, I do think it is worth perhaps mentioning, if you're in a position where performance is not of great concern to you, you can probably get away while learning assembler to use unaligned moves all the time. However, it becomes bad practice in the sense that you're obviously trying to use assembler, if you're coding at the assembler level, to make sure you can maximize performance. And by unnecessarily using an unaligned move, you could be throwing away free performance that could be easily achieved by just ensuring that alignment. But that aside, let's look at how we can actually use one of these moves. So here we have an example of an unaligned packed move of floating point numbers. And what's going to happen here is I'm going to load from X into XMM0. Now, this is not going to just load 32 bits as happened in our case of loading a scalar single. Here we're going to load a full 128 bits because we're performing a packed move. So we're going to actually load all of these values into the XMM register. The way in which they will actually get laid out in memory is as follows. If I have my XMM0 register, the lower order 32 bits will be storing 12.3, then 9.3, 128.2, and then lastly 0.1. So this being the lower order bits, so this will be the 0 to 31, the 32 to 63, and so on. Okay, so that's what happens when we perform this move. And in a single move instruction, we loaded a whole 128 bytes into that register. If we now want to move the other direction, pretty much the same. Say I want to go from XMM15 into A, and I'm going to perform an unaligned move of packed data, and all the values are going to be of 64 bits in size. What will end up happening is it will take my XMM15 register, the bottom 64 bits will get loaded into this location. My top 64 bits will be loaded into this location here. Now again, as I've reiterated many times, sizing in assembler is very important. If, for example, XMM15 had 4 floats stored in it as opposed to 2 doubles, and I performed this move operation, I will end up getting garbage stored across because it would have not correctly transferred the data in the manner I expected. Okay, it would have destroyed this nice separation that I was anticipating because it's thinking it's loading 2 doubles where I actually had 4 floats, and it's likely not going to behave the way you expect it to. So how do I actually perform a packed move? I mean, I showed you an example of an unpacked move, and we can do this if we have our data in a data segment quite simply by simply using the align keyword followed by the multiple we want before the address of the data that we want to be on a 16-byte boundary. What align actually does is it will zero pad the memory locations between X and what came before. So say I had another bit of variable here, say it was a data quad with a value of 17. It will add sufficient space between A and X such that X starts on a 16-byte boundary. Kind of does that calculation for us, which is quite handy. If I'm working with dynamically allocated memory, you'll actually see when we get to that in the next lecture that things like malloc actually do us a bit of a favor, and they always provide us with the initial address being on a multiple of 16 to ensure that we have the ability to perform aligned moves if we want. But if I want to perform an aligned move with this example, and the data is in fact aligned, all I have to do is load x into xmm0, and it will load these values into my xmm0 register. Now, things can get a little tricky when using an aligned move, because if you have memory that has potentially a lot of things going on, it might be a situation that aligned moves sometimes work and sometimes they're segfault, and that's simply a result of the fact that where that memory happened to lie may no longer be on a 16-byte boundary for a different run of the algorithm, depending on what other bits of code you changed. So it is something you need to be mindful of, in the same way in which you could get a segmentation fault by iterating one element outside of an array, and 3 times out of 10 maybe it works fine, and the 7 out of 10 times it didn't work, and it's simply a result of how all the memory is laid out, not just the one thing in isolation. So now that we can move floating point values around, obviously we would like to be able to do something a little bit more complicated than just moving. So we're going to go through how we can perform some primitive operations, specifically addition, multiplication, division, and so forth. What's nice, at least, in that the manner in which I perform all of those base operations is pretty much the same across all of them, unlike with integer operations where there were some slightly more intricate operations, like division was a little bit more complicated. There were multiple versions of multiply and things like that. Okay. I should also make it clear that we don't distinguish between a signed and an unsigned calculation with our floating point numbers, because all numbers are in the IEEE format, which means they're signed by default. So the first thing here is the add instruction. And again, the biggest thing here to get used to is how the mnemonic is formulated, but once you see the pattern, it's very straightforward. So the first one we have here is this add. Specifically, the next letter S indicates we're going to be adding a scalar, and then the last S is to indicate we're working with a single, so a floating point number. So as the instruction here says, it will add a scalar float to another scalar float. If I have a D at the end, it will add a scalar double to another scalar double. If we use the packed versions of the operations, we add 4 floats to 4 floats in the case of working with singles. And in the case of doubles, we will add 2 doubles to 2 doubles. And this addition happens in a pairwise fashion, which you'll see in this example at the bottom. Now, this operator takes 2 operands. The one is the destination, so the left-hand side is the destination and the right is the source as normal. However, there's a little bit of an extra restriction at play here when we're talking about floating point calculations, and that is that the source can be at least memory, or it can actually be an XMM register. However, the destination must be an XMM register. Or if you're talking about the equivalent version of this calculation with the YMM registers, then it also has to still be a destination being a register. So with floating point calculations like add, subtract, multiply, the destination has to actually be a floating point register. It cannot be a memory location. So it's an easy place to make a mistake. Obviously, the assembler will throw an error at you if you try and run this code, but it's a place you can make an error in an exam or a test that you need to learn to avoid. That floating point operations do not allow you to have a memory location as the destination. Okay, unless it's a move instruction, obviously, but in terms of the calculation instructions, it can only be a register. The other thing that's a little different to our integer corresponding operations is that flags are unaffected. So before, if I added 2 numbers, I could be setting a sign flag or a 0 flag. In the case of floating point calculations, we do not set any flags as a result of calculations. Okay, so that's something to keep in mind, and it will come into play when we talk about comparisons, obviously. So here's a little example of doing something simple with floating point numbers. I'm going to load A into XMM0. Specifically, it's going to be a scalar single. So for this to have this code to work, A would have to be a 32-bit value. I'm then going to add XMM0 to B. And again, I'm going to perform an add using a scalar single. So basically what's going to happen is it's going to add this 32-bit value at location B to the bottom 32 bits in XMM0 and store the result in those bottom 32 bits of XMM0. Say I want to store the result in my data segment again. All I have to do is perform a move SS going from XMM0 to C. So in this case, assumedly C would be sufficiently large to store those 32 bits. And because I actually performed only a single scalar move, I'm only going to be extracting the bottom 32 bits out of XMM0. How can I perform a packed type of calculation? Well, it's relatively straightforward. So here I'm performing a move from A into XMM0. We made the assumption that A is on a 16 byte boundary. If we didn't know that, we would use U. Then I'm going to perform an add operation. So add packed double. So basically, because I'm about to work on a 128-bit register, it means I'm going to be doing a calculation with two 64-bit numbers. And I'm going to be adding that to B. So in essence, what's going to happen is we're going to look at what is in XMM0. So we have our two values. So let's call this one over here a 0 and this one a 1. And this register is our XMM0 register. Then if I perform the add against B, it's going to perform an addition using the first element. So this will be the lower 32 bits from location B, and this will be corresponding to the higher 32 bits from location B. And I'll perform pairwise addition. So basically I'm going to add this term to this term, and in the lower 32 bits of XMM0 will end up being A0 plus B0, and then in the higher 32 bits we'll end up having the result of the calculation of A1 plus B1. And that's really where the power of the packed operation comes in, because that add takes the same amount of time as that add to actually perform the calculation, which means I'm able to perform, in this case, twice as many additions in the same amount of time. And this extends greatly if, for example, I'm using the larger versions of these instructions. So if I'm using the YMM version and only talking about floats, suddenly I can perform 8 floating point operations in a single calculation. Now, just as a recap, in terms of what I would have to change if I wanted to work with my YMM registers, all that would have to change is, for example, if I was going to perform a move with them, I would end up having to say I wanted to make this with this the equivalent operation. I would simply go V mov SS, or more likely I'm going to be changing the add operation. It's just simply going to be add DD SS and so forth. Okay, actually rather these operations are more akin to the situation where I'm talking about packed data. Sorry, so if I want to perform a packed move with a 256-bit version of these registers, so the YMM versions, I would simply use a vmov APS for an aligned packed move of signals, and if I wanted to perform the addition, it would just be add P singles. The change is that I just simply have to add that V. Okay, so again, simply adding the V will allow us to work with the YMM versions of these registers. So how do we perform other operations? Well, luckily for us, it's pretty much the same the whole way through. So if I want to perform a subtraction, same situation applies. So I have sub for subtract, S to indicate it's going to be a scalar, S there to indicate it's a single. The same thing applies, single, double, packed, single, packed, double. And I can perform calculations exactly as I could have in the previous example, just now I'm subtracting as opposed to adding. So here's the list of kind of primitive instructions. We have add, subtract, multiply, and divide. And again, no distinction between signed and unsigned, all of which work in the same kind of way. Now, one thing that you need to also be aware of is that I cannot add two floating point numbers if they both occupy different number of bits. So I cannot add a 32-bit floating point number directly to a 64-bit floating point number. If I want to do that, I need to convert them such that they are both in the same format size. So I could either convert the 64-bit number down to 32 bits, then perform my calculation on the two 32 bits, or I could upscale the 32-bit number to the 64-bit number and perform my calculation there. Upscaling will probably be better in the sense that you don't lose any information in that process, but it depends on the situation you're in. So the conversion to actually go from a single to a double or a double to a single is an instruction that looks relatively lengthy, but again, as soon as you remember the mnemonics, they're easy enough to actually remember. So we start with CVT for convert. What's on the left here indicates what you're converting from. So I'm going to convert from a scalar single, so I'm only dealing with one float, to, so I'm going from one float to one double, because it's a scalar double. So this will convert a single scalar to a single double, or sorry, a scalar single to a scalar double. If I want to perform a more general version of this, I can do a packed type of calculation as well. So I can convert from a packed single to a packed double. This will convert two packed floats to two packed doubles. Now what is interesting there is that when I perform this calculation, you'll note that I went from two packed floats to two packed doubles, but I could have in principle stored 4 floats inside an XMM register. The problem is I cannot convert 4 floats into 4 doubles and still have them live in 128 bits. Okay, so that's why we end up going from 2 packed floats to 2 packed doubles. I can also convert the other way around. I can go from a singular or a scalar double to a scalar float. So I'm going from a 64-bit floating point number down to a 32-bit floating point. And in the same vein, I can convert packed doubles into packed signals. Again, this will convert 2 packed doubles to 2 packed floats. This conversion instruction obviously is designed to work with the XMM registers. If I wanted to work with the YMM registers, I would simply again add a V. So for example, it could become quite a lengthy expression. So I could, for example, do this, which would actually convert 4 packed doubles into 4 packed floats. But again, for the most part, you don't have to worry too much about that version of the instruction. So we can see a bit of an illustration here at the bottom. So I'm going to convert a singular double at location A into a scalar double. Okay, so scalar single to a scalar double, and I'm going to store it in XMM0. So the bottom 64 bits of XMM0 are going to store the upscaled version of this 32-bit float that would have been at location A. Once it's done that, I can, for example, add my XMM0 with B. Let's assume B was storing a 64-bit value. So I could now perform my addition, and now say I wanted to get the result back down to 32 bits because maybe that's what I needed its size to be. I'll simply convert from the double, so a singular double, to a scalar single, and now the bottom 32 bits of XMM0 are going to contain that floating point number, whereas before this instruction they contain the 64-bit version of it in the bottom 64 bits, and then I can simply move it out of XMM0 into C again because it's a scalar single. It's going to just move the bottom of 32 bits. It is also obviously going to sometimes be important to be able to convert from integers to floats. As I mentioned before, you may be in a situation where you need to multiply, say, a floating point number by an integer, and obviously then we need to have them be of the same type. I need to have both be of type floating point number if I want the result to be a floating point. So how do I go about doing that? Well, again, we have a similar kind of mnemonic available. We have this CVT. Again, we have our starting format. So this is going to convert a scalar single to a scalar integer. So this is going to convert a float to a double word or a quad word integer by rounding. Okay. Now, this is where things get a little bit intricate because how am I going to determine between whether it's going to convert to a double word or a quad word on the integer side? So I went from something that was explicit. I mean, on this notation here, it clearly indicates that I'm talking about one 32-bit floating point number. But on the right-hand side, I'm simply saying I have a scalar integer. what actually happens is that the assembler uses the register that you are storing the result in to determine it. So in the case over here, this CVT SS2SI is going to convert a scalar single from XMM0. So this is the bottom 32 bits we're working with. And it's going to store the result in a double data word because this is a 32-bit register. If I use the exact same instruction and I just turned that EAX into an RAX, it would convert it into a quad word. So again, it's figuring out the size of the integer based on the register. So there's a couple of things at play here. We're explicitly saying the size of the floating point number, but we're actually implicitly indicating the size of the resulting integer based on the register size. Obviously, we want to be able to convert the other way as well. So I can convert from, say here, I can convert from an integer into a scalar signal. And this would convert a normal integer value into a 32-bit floating point one. The question again is what size integer are we working with, and it will actually now, once again, determine or derive this based on the register size. Okay, so you'll see at the bottom here, I'm converting from this way over here, I'm converting from an integer into a double data word, into a double floating point number, because it's a scalar double, and it's going to convert from a 64-bit integer into a 64-bit double because we're dealing with a 64-bit integer register. Now the question is, what happens if I don't work directly with a register as the right-hand operand then? Say I wanted to work from memory. That's perfectly fine, but you have to specify the size. So in this case, say X was 32 bits, I would have to use dword to indicate the size because the instruction itself does not contain enough information to infer that from. If X was in fact a quad word, then I would simply use quad word over there. Okay. You'll see often if you do any kind of numerical calculation, you're likely to, for example, have a loop variable that's going to be an integer, and that loop variable could be used in the calculation that's going to be against a floating point number. So you actually will encounter this conversion more frequently than you would have in, say, C++. And the simple reason for that is that we have to be very explicit about our data type conversions in assembler. Whereas in a language like C++, generally speaking, if I multiply a float by an integer, there's a process called coercion that happens where that calculation is turned into a float because it's kind of inferred that's what we want. So it actually does a casting of the integer before it does the calculation for us. So that's something to keep in mind. But in assembler, obviously we have no compilers to help us. We have to do everything ourselves and think of everything ourselves. Now, the next thing we need to actually be able to do with floating point numbers is comparisons. Okay? I mean, we discussed how we can perform comparisons in normal integer type calculations. I mean, that's how we performed if statements and jumps. And we can use a similar kind of idea when it comes to floating point calculations, except we have to use a slightly different type of jump and a different comparison. Because remember, the comparison operations that we discussed before was in essence performing a subtraction, but didn't store the result. Now we want to do something similar here with assembler, so we want to perform kind of a subtraction and use the result of that to actually set flags. But firstly, subtractions with floating point numbers don't set flags, so we need a more specific instruction to use. And also, the type of comparison operation is likely going to be different because it needs to discern whether it's performing a subtraction type operation using integers or floats. Now, with that in mind, there are two types of comparisons available to us in assembler. There's an unordered and an ordered comparison. Okay. Now, in the IEEE 754 floating point standard, there are actually two types of nans. Okay, so two types of not numbers. There's what's referred to as a QNAN and an SNAN. A QNAN means it's a quiet, not a number. So basically, the result of the calculation is not a number, but the program doesn't scream at you telling you that something horrible has gone wrong. Whereas an SNAN is what's referred to as a signaling, not a number. So this is the type of NAN that is clearly going to be problematic and it will halt the program execution. Now, both in terms of the bit encoding are quite similar because both have all exponent fields set to 1 and the QNAN has its top fraction bit equal to 1. So that's the only distinction between the two. Now, the reason I bring this up, it's a bit of a subtle distinction between a QNAN and an SNAN, but in languages like C++, which are compiled using G++, or in our case, if we're compiling against C, we use GCC, we actually utilize unordered comparisons because we don't throw exceptions unless we get a signaling NAN, which is why sometimes you can perform calculations and you have a minus infinity sitting in a variable and the program hasn't complained at you because it hasn't triggered a signaling NAN. So the only reason we bring up this distinction between quiet NANs and signaling NANs is just to make it clear that we are going to work for the purposes of this course with unordered comparisons, which basically are comparisons that will work perfectly fine provided we do not encounter a signaling NAN. Okay, so that's why we have the unordered comparison, and this is perfectly in line with what GCC and the similar ones do. You'll actually not often encounter an ordered comparison in modern day code. Now, if I want to perform a comparison between two different floating point numbers, I have to specify what size the floating point number I'm about to compare against is. So am I comparing two 32-bit ones or two 64-bit ones? And I do that by indicating at the end this S to indicate that it's going to actually be a single that I'm comparing, so two 32-bit numbers, or D to indicate I'm comparing two 64-bit numbers. And you'll see here we have this U in front to indicate as an unordered comparison. Okay, so we have an unordered comparison of singles if we're comparing two 32-bit floats, or it's an unordered comparison of doubles if I'm comparing two 64-bit floats. Now there's a couple of extra restrictions. The first is, much like addition and subtraction with floating point numbers, the first operand must be a register. Okay. Again, there is the version of this where we simply append the V in front if I'm talking about the YMM registers, but we're focusing on the XMM ones for the moment. So here we have a little example. Now, the first thing I should make clear is that when I perform a comparison, an unordered comparison or an ordered one for that matter, it sets flags. Specifically, it sets 0 flags, parity flags, and carry flags. Now, with the use of those 3 flags, we can actually determine whether the left-hand operand was less than, equal to, or greater than the right-hand operand. So we'll see here that I want to perform a comparison between two 32-bit numbers. So in this little example, I want to perform a jump if A times B is less than a value C. Okay, where A, B, and C are all 32-bit floats in our data segment. Okay, so I'm going to load A into XMM0. So again, it's loading A into the bottom 32 bits of XMM0. Then I'm going to perform a multiplication of A with B. And the result will be stored in the bottom 32 bits of XMM0. So basically I did this calculation here. Then I'm going to compare XMM0 with C. And if I'm in a situation that what is on the left-hand side is below or equal to what is on the right-hand side, I'm going to jump to this label. And that's where this BE comes from, below or equal. Now, remember before with integer-based comparisons, we had that table of all the kinds of jumps that we can encounter. The same situation exists with regards to floating point operations. So the type of jump you use is not the same. If you're performing a floating point comparison, you need to use a jump that relies on the corresponding floating point flags. So you'll see here, we have the more common mnemonics. We have JB for jump if below. So basically we have two operands. So let's just say A and B. It will jump if the left-hand side is below the right-hand side. So basically if A is less than B. We then have JBE. So we're going to jump if A is below or equal to B. So in essence, it's less or equal to. We then have JA for jump above if it's greater than. JAE for greater than or equal. Then we have JE for jump if they are equal. And then lastly, we have JNE of jump if they're not equal. There are certain aliases that are used a little less commonly. For example, JZ for jump if 0 is the same as jump if equal. And you can also have not above, not below or equal, or not below. There's also the versions where we use just the carry flag. You will not encounter that much in practice because it's a little unclear what you're trying to test. It does obviously work, but it's not as transparent as the other instructions. Something I think I should just maybe remind you of, which we actually mentioned in chapter 2, but relying on perfect equality with regards to floating point numbers can be dangerous because we have a lot of imprecision when working with floating point numbers, and two numbers should have actually become equal during the course of some calculations, but they might be off by 1 bit, and as a result they will not come across as being equal, though the difference is negligible. So that concern is still just as prevalent in the case of assembler as it is in a higher level language. So if you want to deal with floating point equality more precisely, again, you check whether or not A is within an epsilon of B. So basically in assembler you would need to check, is A minus B less than some kind of epsilon, where epsilon is, say, the precision of the machine. So this could be something like 0.0201. Okay, now obviously for simple programs that's maybe not a concern, but I think it's worth mentioning that just because we're working in assembler, this issue doesn't go away. We still have to address it if we have numeric computations we want to perform. Now, something that is a little bit sad is that with modern floating point instruction sets, we've lost a lot of the built-in functionality that was available to us. So on the old 8086 chip, there was specific instructions for performing sine, cosine, arctangent, and many other trigonometric functions, and even more just generic type of calculations. However, these new instructions are omitted on the XMM registers. You can still use these sine, cosine, and so on instructions with the floating point stack, which we don't explicitly cover because it's not in use anymore. But on the XMM register side, we don't have those available. So instead, we have to implement them ourselves. And generally speaking, you implement them yourselves once efficiently, and you can continually use it from there. There's actually a lot of algorithms online for how to implement sine efficiently and cos efficiently. It's kind of its own little subfield. In the days of the 8086, those algorithms I mentioned were hard-coded into the chip. Now we have to emulate them via software, but it's very trivial to actually do that kind of emulation now anyway. There are a couple of instructions, however, kind of calculations that are given to us with the XMM instructions. So not everything has been stripped away. These are the ones we have available to us. We have the minimum, maximum, a round instruction, so we can round up or down, square root, and a reciprocal of a square root. So basically, just for contrast, it's simply, well, whatever variable will be. Let's call this a, 1 over square root of a. We have that available to us as well. So square root is often used, so that's why it's provided to us, and you'll see square root is actually used quite frequently in calculating many other functions, such as the trigonometric functions that were listed up here. So hence why it was actually given to us even in the XMM realm of instructions. So let's look at a little example of one of them because they work in very similar ways, and all of them have packed and scaled, or sorry, packed versions and scalar versions. So let's look at the min and max because they're quite useful performing if you want to do checks across many floating point numbers. So here we have, say, the max operand, so max SS, so again, scalar single, and it's going to be looking for the maximum of scalar floats. Okay, so given two floats, it will store the larger of the two in the destination register. Again, for this instruction, as with the adds and subtracts of the floating point numbers, the destination operand must be an XMM register. The source, however, can be an XMM register or memory. Again, if you want to use the Y versions, we just have to add that V. And what it will do is it will simply store, in the case of, say, minimum, the minimum of the two floats in the lower order register. That's not that exciting, however. What is more exciting is being able to perform the same calculation using packed. So here we have max PS, so it's going to be a calculation based on packed scalars, or we can perform a calculation based on packed doubles. So how does that actually work? Well, let's consider the min version, min PS, so min packed scalar, and say I pass through it, sorry, min packed single, say I pass to it XMM0 and XMM1, it will compute 4 minimums and place them in XMM0. Okay, so basically what will end up happening there is, say I have, I'm just going to use integer numbers because they'll be shorter to represent, but these would obviously be floating point numbers. Say I had 7115 in XMM0, and then I had, say, 1339 in XMM1. And I performed this instruction over here. What would end up happening is I would store my result in XMM0, and each one of the elements will correspond to the minimum. So in this case, it's going to be 7. In this case, it's 1, 1, 1. And what's amazing about this type of calculation is that it stored the minimum of those 4 floating point numbers in a single clock. Okay, so I was able to perform 4 calculations using a singular clock, which is why doing things like this are so efficient. Here we have a slightly more complicated example. So I'm going to perform a move of x into XMM0. So it's just a scalar single. And then I'm going to perform the max of XMM0 and y. And basically this is just going to set the lower 32 bits, because remember it's a scalar I'm working with, of XMM0 to be the maximum of x and y. Simple enough. If I am doing a similar kind of calculation but with the packed versions, it gets a bit more complicated. So I want to perform a packed move. So in this case, I'm going to perform an aligned move from A into XMM0. So I'm loading 2 doubles into XMM0. Again, we're assuming A is on a 16-byte boundary because it's an aligned move. Then I'm going to perform a min PD calculation. So again, minimum packed doubles using XMM0 and B. So for this to work, B will have to actually be 2 64-bit values. And in essence, what's going to happen is the lower 64 bits of XMM0 are going to be set to the minimum of A0 and B0. So basically the lower order bits of A and the lower order bits of XMM0. And in a similar fashion, XMM0, the higher 64 order bits, will be set to the minimum of A1 and B1. So it's exactly the same kind of situation that we encountered over there. We also have rounding, which is quite common. You obviously don't see this in higher level languages, but it comes up more frequently when you work on an assembler level. Well, obviously you can still round in a high level language. You're just not often required to do it as frequently as in assembler. So here we have a round SS. So again, scalar single, so 1 floating point number. PS for packed single, so this will be 4 floats because this is a instruction designed to work on the XMM registers. Again, we would use vround PS if I was working with 8 floats and a YMM register. Here we have round SD for a scalar double, round PD for a packed double. In this case, it will simply be 2 doubles. So I can round a singular value or all the values that I have in my register. The first operand of this instruction must be an XMM register. Obviously, if it's a V version of this instruction, you can use the YMM register. The second operand must be the source, and it can be either an XMM register or memory. And then lastly, we have to specify the mode of rounding. So we have 4 modes available to us in terms of rounding. We have mode 0, which you just specify with an immediate value. So you actually literally will have something like round, sorry, my handwriting is quite terrible, round, say SS, XMM0. So say I'm rounding, the result of my calculation is just going to go into XMM0, and say the value I wanted to round was already in XMM0. I will simply specify the mode as the last operand as an intermediate value. So I just put the digit in place. Okay, if the mode is 0, we round giving ties to even numbers. So if we're halfway between 2 numbers, we will round towards the even number. If we use mode 1, we round down. So we always round in the negative direction. If we use 2, we will always round up. And in the third case, we will round towards 0. So basically, if I have 0, 1, 2, minus 1, minus 2, so this is a little number line, I will always round towards 0. Okay, so if I had 1.5, I will round to 0. If I had minus a half, I will round to 0. Sorry, I misspoke. If I have a half, I will round to 0. And if I have minus a half, I will round to 0. So always round towards 0. If I had, as I incorrectly stated earlier, if I had 1.5, I would round towards the 1, but it's in the 0 direction. Okay, so I'm always rounding in the 0 direction with mode 3. We also have, obviously, some of the other calculations. We have our square root, pretty much exactly the same as our round, except we don't have a third operand to specify mode because square root is relatively well defined. Let's look at a quick example here. So here we have a function which is the distance in 3D. So basically it's just the Euclidean distance between 2 points. Okay, so I have point 1, which is x1, y1, z1, and I have point 2, which is x2, y2, z2, and I want to check the distance between the two of them. So in essence, it's just an extension of Pythagoras' theorem. So let's see how we could do that using floating point calculations. Now, something I should make clear here is the function prototype that is at play here is as follows. So I'm going to be returning in this case, if I look, it's going to be a float. So it's the same as having float distance 3D, and the parameters that are being passed here, the textbook has a similar example to this, they just don't make this clear, is we're actually passing through 2 pointers. So let's just call this A and this one B. Now, when I pass a pointer to a function, I'm actually passing that pointer in an integer register because a floating point number, a pointer is in fact just an integer. So what's actually happening for the sake of this example is that we're passing through 2 arrays that are represented using float stars. But because I'm passing this through as a pointer, my value that is being passed through is an integer, which means I'm going to be using the first and the second integer registers of my normal functional ABI from the previous lecture. So don't think that I'm passing, in this case, 6 floating point numbers through for this example. I'm passing through 2 floats. Okay, so I just want to make that clear. I'm passing through 2 float arrays rather, so 2 float stars. The only thing, obviously, here we don't explicitly state how many elements are in A and B. It's kind of just assumed in this code that there's always going to be exactly 3. So here, first thing I'm going to do is I'm going to extract my first element from RDI into XMM0. So basically, this is getting out from RDI. Remember, RDI is going to point to A. It's going to extract the first element of the array A. Okay, I'm going to move this into my XMM register, and because it's a singular scalar, it's just going to move 32 bits across. Then I'm going to subtract from XMM0 the first element at location B. So basically, I'm just deregistering the pointer at its index location 0. So this is basically, this would correspond to B0. Okay. I'm subtracting it and storing the result in XMM0, and that's basically performing that calculation over there. So I did the subtraction. Now I'm going to square it, so I'm going to multiply the register with itself. Again, because I'm performing a scalar single calculation, it's only going to be doing these calculations using the bottom 32 bits. Then I'm going to repeat the process for the second and the third element. So here, I'm going to extract, in this case, it's going to be A1 that I'm extracting. And I'm going to store this in XMM1. Then I'm going to extract B1, and I'm going to subtract that from A1 and store the result in XMM1. Now you'll note here the step sizes, okay? And that's because we're dealing with floats. Remember, each float is 32-bit value, so if I want to get to the next float, all I need to do is add 4. Once again, I'm going to square that subtraction to get this second term over here. So basically y1 minus y2 squared. And then I repeat the process for my third element, the distinction now being I use plus 8 because it's going to correspond to A2 and B2, and remember each floating point number is 32 bits. Then we square it again. The last thing we have to do is we simply have to add them up. So I'm going to add xm0 to xm1. So basically I'm performing the addition between this term and this term. And then lastly, I just want to add the last square to it. So I'm going to add another add ss from xmm0 to xmm2. Store the result in xmm0. Last step is I just need a square root. So I'm going to simply use sqrtss because again it's a scalar single, and I'm going to store the result in xmm0 and return. Now remember, the return variable, floating point variable, will be xmm0. Just like with integer calculations, RAX was our return value. For floating point operations, we store the result if we expected to get a float back in xmm0. That's the default register we use as our return register. Let's do another somewhat similar kind of calculation. Here I'm performing the dot product. So basically the dot product is just the same as me going A dot B, which would be the same as going AI times BI across all of the elements. Okay, so in this case it's just I equal to 1 into up to 3. Okay, so in this case I'm just performing the dot product between two vectors. In this case we have first component, second component, third component, and so forth. The indexing here doesn't correspond perfectly because of the way this is set up. So our two vectors at play here would be, again, it will be x1, y1, z1, x2, y2, z2. So the dot product here will just be x1 times x2 plus y1, y2 plus z1, z2. Okay. And to do that, same as before, we simply, again, this example is set up such that basically the prototype would be float dot product float star A, just for simplicity, float star B. So once again, we're working with pointers here. So if I want to gain access to the first element, I simply extract it from RDI, because remember RDI contains the first parameter to a function. In this case, it happens to be a pointer, and we use the square brackets to dereference the pointer. We move this into xmm0. We move the B element, or in this case, it will be corresponding to B0, into xmm0. We then do the same thing. Well, in this case here, we are multiplying. Do the same thing for the next pair. So basically I move out the 1 and I multiply with the value from B. I then add it to my calculation that I did over here, and then lastly I extract and do the multiplication for the third elements of the two arrays, and then I just have to do the last addition. So basically I've already added these two together. I'm now going to add it with that term, and the result of this calculation has already been put into xmm0, so I can simply return. Now, something I want you to try and do as a bit of a homework example is imagine that we wanted to perform this dot product on 4 or elements or dimensional vectors of size 4. So instead of having just x, y, z, we have x, y, z, q, and I want you to perform a dot product with a 4-dimensional value. So basically vectors of size 4. Now, obviously you could do that the same way that we've just done this example, where I do it component wise. However, what I want you to try and do is to do that calculation using packed versions of move and multiply. And you'll see that I can actually do this in a very quick fashion, because I can actually perform the multiplication across all elements in one go. And then there's a little extra instruction that you can do a little bit of searching for, which will actually add across the registers. It's not critical that you know that, but it's a nice illustration of how you can do that kind of operation very quickly. Now, it does sometimes feel like it's a little overwhelming when you get to floating point numbers, and that's because we've introduced two things here. We've introduced floating point calculations and summed instructions at the same time, so it may take you a little bit of time to get used to. But doing simple floating point calculations is pretty straightforward if you just think about the fact that you're only using the bottom part of the registers. It gets a little bit more complicated when we try and use packed instructions, when we're trying to get that performance. But it's definitely a place that's worth spending your time, because this stuff will come up quite frequently but also if you actually implement real-world assembler, it's very likely going to be in the context of numerical computation, and that's where these instructions really show their power. Okay guys, that brings us to the end of today's lecture.